Large language models have given malicious actors the ability to automate and rewrite their own code at a pace that breaks traditional cybersecurity defenses. By 2025, LLM-assisted malware will reach 50% of threats, up from 2% in 2021. Attackers use AI to scale polymorphic malware. The model outputs a script, tests it, and mutates the code, slipping past static, signature-based filters. Stopping an attack that interprets and rewrites code semantically requires defensive systems that can process logic with that same transformer-based speed. The cybersecurity landscape has settled into a symmetrical arms race. Threat detection relying on human speed analysis is no longer viable against AI-augmented adversaries. This automated defense must happen inside the enterprise DevSecOps pipeline, the environment where code is continuously integrated and deployed. But connecting an enterprise security stack directly to a commercial, centralized API introduces systemic vulnerabilities. Routing proprietary source code, system telemetry, or personally identifiable information to an external cloud model violates strict data residency requirements. Transmitting this data offsite triggers compliance failures under regulations like GDPR and the California Privacy Act. There is also the risk of data extraction, where an adversary could theoretically reverse engineer sensitive corporate data from the centralized model's training set. Solving this paradox requires a localized architecture that keeps both the model and the telemetry entirely within the corporate firewall. The first requirement for a Defender LLM is a transition from rule-based detection to semantic analysis. This diagram compares the two approaches. On the left, the traditional pipeline relies on static analyzers, which check code against strict, predefined rules and known attack signatures. If an attacker deploys a zero-day vulnerability, a flaw with no existing signature, the static analyzer misses the threat. Looking at the LLM-enhanced pipeline, the system applies semantic code understanding. Using contextual embeddings, the model understands the intent of the code. It identifies subtle logic flaws and control flow anomalies, flagging zero-day threats through predictive modeling before they ever execute. Semantic analysis changes code scanning from reactive historical matching to proactive logic validation. The challenge is performing that deep semantic scan without exposing sensitive enterprise data to the cloud. This diagram details how federated learning addresses the privacy bottleneck. In the centralized system on the left, user data transmits directly to the cloud, creating compliance risks. Federated learning on the right distributes the model to local nodes, like edge devices, instead of centralizing data. These local models train on raw telemetry and anomaly data natively. Private information stays behind the firewall. To improve the global system, only encrypted gradient updates, mathematical adjustments to the model's weights, are sent back to the central server. Federated learning decouples AI utility from data exposure, allowing enterprises to leverage LLMs while maintaining compliance by design. If a localized LLM flags a critical corporate service as malicious, security analysts must be able to verify the logic behind that decision. In high-stakes DevSecOps environments, an opaque probability score is not a sufficient reason to shut down production code. This infographic outlines the explainability tools required to build operational trust in these systems. The top tier, model-level interpretation, utilizes frameworks like SHAP and LIME. These tools use token attribution to map exactly which lines of code or attention patterns triggered the vulnerability classification. Integrating explainable AI transforms the LLM from an opaque oracle into a precise, auditable diagnostic tool. This complete Defender LLM pipeline utilizes semantic code detection localized through federated learning, outputting its reasoning to an auditable explanation dashboard. This architecture provides zero-day threat detection while mathematically preserving data residency and human oversight. These technical requirements are rapidly shifting from security best practices to strict regulatory mandates. This timeline shows the emerging global standards demanding model transparency and structured risk assessments. The 2024 release of the NIST AI Risk Management Framework establishes requirements for data provenance and safety constraints. Similarly, the EU AI Act mandates transparency and auditability for high-impact algorithmic models. Deploying off-the-shelf, centralized black box AI models in an enterprise setting will soon directly violate these impending legal frameworks. To secure the digital frontier against AI-augmented threats, Systems architects must integrate privacy and explainability into the core technical requirements of their defenses.